Okay, this is the third video on integrating rational functions by partial fraction decomposition. In the last video, I showed you how to solve this particular problem. And what's going to be different about the one we're going to do now is the way that the denominator factors. On this one, we have what are called distinct linear factors. All of my factors are degree 1 polynomials, and none of them are repeated in that I don't have the same one twice. Had this been x plus 2 quantity squared, it would have been a repeated linear factor. And that will affect how we break down the problem of a partial fraction decomposition. So I'd like to give you an example now where one of the factors is repeated. So I'm going to go ahead and just give you one where it's already factored. For simplicity, in general, the denominator won't be factored for you, but let's just go ahead and assume we know how to do that. So how about the integral of x over x plus 1 quantity squared, and then we'll throw in a distinct factor as well, just to keep us honest. So we'll take this one for example. So now I'd like to rewrite this as a sum of fractions, just using the factors in the denominator. So this is the actual partial fraction decomposition. Now this distinct linear factor, we're going to treat this the same way we did in the last problem. That's going to give me a constant over x plus 2 in my decomposition. Now, this guy is squared. Now typically what one would do here, since this x plus 1 quantity squared is a degree 2 polynomial, what should go up the top is, at worst, a degree 1 polynomial. So the theory tells us that we should put a bx plus c here. But there's an algebraic trick one can do, which I'm not going to go through in this video. But one can actually modify this and make our problem a little bit easier by not using bx plus c over x plus 1 squared, but by doing the following. We're going to end up with two different terms over here, one with x plus 1 and another with x plus 1 quantity squared. Now had that x plus 1 been cubed, I would have an x plus 1 term, an x plus 1 squared, and a third x plus 1 cubed term. Now what do I put in the numerator? And this is the beauty of it, we just need a constant in both of them, b and c. Had this been x plus 1 to the third, I'd have another term plus, let's say, capital D over x plus 1 to the third, or pick your favorite letter. But this actually, as it turns out, is going to end up working. And once we get the numbers for a, b, and c, we'll be able to integrate this one term at a time. We know how to do this one, we know how to do this one, and this we've actually seen before. Okay, so how about finding the a, b, and c? Well, fortunately, we started the same way as we did the last one. We're going to multiply both sides by the denominator of the big fraction, and that's going to clear out all fractions in this equation. So if I multiply both sides by this denominator, I'm going to get x on the left. Now when this term gets multiplied by this denominator, the x plus 2's are going to cancel, but the x plus 1 squared will not. So I'll get that. When I multiply the second one of the x plus 1's will cancel, the x plus 2 won't, neither will the other x plus 1. So I'm going to end up with one copy of x plus 1 and one copy of x plus 2. And on the third one, both of the x plus 1's will cancel, the x plus 2 will not, and we'll end up with this. Now, as in the last case, if I pick a value for x which corresponds to a root of one of these terms here, in other words, x equals -1 or x equals -2, that's going to simplify the solution process significantly. So I'm going to start by doing that. Let's let x equal -1. Plug it in everywhere for x and just get a specific equation. On the left-hand side, we'll get -1. Here we'll get 0. Here we'll get 0. And then -1 plus 2 is 1, so I'm going to get c there. And we just get c equals -1, so we almost got c for free. Similarly, plugging in x equal -2 will also cause a lot of things to cancel out. So let's try that on the left-hand side, I'll get negative 2. On the right-hand side, I get negative 1 squared, that's 1. So that's going to be A. Over here, 0 times anything is 0, that will be 0. And then over here, negative 2 plus 2 is 0, times C is 0, 0. So I just got A almost for free. Now all that's left to find is the value of capital B. And I'm going to need another equation to get it. Now I've already used up negative 1 and 2 for x, so I'm just going to pick a third choice. There's no natural choice anymore, so I'm going to just use the easiest number to work with that I haven't used yet. I think x equals 0 is probably going to be the simplest, but it doesn't really matter what we use here. So if I plug in 0 everywhere for x, I'm going to get 0 here on the left. Here I get 1 times A, but A is negative 2, so I'm just going to get a negative 2. 1 times negative 2 is negative 2. Here, I'm getting 1 times 2 times B, so I'm getting 2 times B. And here, I'm getting 2 times C, but C was negative 1, so 2 times C is negative 2. And now I have one equation with one unknown. I can solve it for B. This turns into 2B equals 4, so B is 2. Okay, so now, getting back to the original problem that we were trying to solve, this becomes the integral of A over x plus 2, but A was negative 2. So negative 2 over x plus 2. Plus B over x plus 1, B was 2. Plus 2 over x plus 1. And then C over x plus 1 squared, C was negative 1. So minus 1 over x plus 1 squared. Now the first two we can integrate without doing a whole lot of work. Negative 2 log x plus 2 plus 2 log x plus 1. But now I still need to integrate negative 1 over x plus 1 squared. This is actually the generalized power rule. So I'm going to break this one up for you. This is minus the integral of x plus 1 to the negative 2. Technically this is a u substitution where u is x plus 1, but its derivative is 1, so I really don't need to spell that all out. So I'm just going to use the power rule on that. So what do? We add 1 to the exponent and then divide by the new exponent. So that's x plus 1 to the negative 1 over negative 1 plus c. And then we like to not leave negative exponents in our answer, so let's go ahead and clean that up. So what do we have? Negative divided by negative 1, that becomes plus, and then 1 over x plus 1 to the first. And here's your